Hello everyone, my name is Rasika Sarwade and today I'll be presenting my project on electrical impedance tomography or EIT as a part of the course Signals and Systems. So, what exactly is electrical impedance tomography? EIT is a portable, non-invasive and cost-effective imaging technique. It helps us to visualize the electrical conductivity distribution inside the body or the region of interest, offering a real-time assessment of ventilation distribution. One of the key advantages of EIT is that it's radiation-free, which makes it safer compared to traditional imaging techniques. It's also useful for bedside monitoring with fast responsiveness. Now, why is EIT important? There are a variety of medical conditions where knowing the distribution of electrical properties inside the body is crucial. By electrical properties, I am referring to the body's electric conductivity and permittivity. One practical example is in the detection of blood clots in the lungs. EIT can locate gas and blood in the body by mapping the conductivity, making it a valuable diagnostic tool. It also has several other applications, such as in the industrial fields. In the EIT process, electrodes are placed around the chest, typically between the fourth and fifth intercostal spaces. These electrodes are connected to a computing device that sends a small alternating current from a reference electrode to the other electrodes. As the reference point rotates around the chest, voltage is measured between adjacent pairs of electrodes, about 50 times per second. These measurements are used to reconstruct a real-time image of the body's internal structures or the conductivity distribution. So, the EIT consists of solving a forward problem and an inverse problem. Basically, in the forward problem, what we do is we inject current and then we take the voltage measurements. And the inverse problem is basically the reconstruction of the image using those measured voltages. Here we have the visual representation of the forward and inverse problem. So as we can see, the current is injected between the electrode number 1 and 16, and then the voltage readings are taken for the other pairs of electrodes, the other adjacent pairs of electrodes, and then we can see that the current is now provided between the electrode number 1 and 2, and the voltage readings are taken for the other pairs of electrodes. We do the same thing for all the other pairs of adjacent electrodes, and then we can see from these obtained voltage measurements we get the electrical conductivity distribution through solving the inverse problem of EIT. Here is the visual representation of the inverse problem. So now moving on to the modeling and simulation part of the EIT. I have personally performed the modeling and simulation of EIT using the software COMSOL Multiphysics. I have considered a cylindrical container, and the cylindrical container is filled with saline water. There is an aluminium material placed in the middle of the cylindrical container with the air cavity in it, and there are 16 electrodes that are placed outside the cylindrical container, which are useful for the voltage measurements that we will need to solve the inverse problem. The forward problem of EIT is solved using finite element method, and this is the result that I have got from solving the forward problem using COMSOL Multiphysics software, as you can see. Now, moving on to the mathematical formulation of the forward problem. The equation relating to the distribution of conductivity and potential within a bounded region with low frequency current flow has the given form, and basically these are the Dirichlet and Newman boundary conditions. The forward operator is basically an operator that maps conductivity distribution to measured voltages, as we can see here. And there is discretization, that is piecewise constant conductivity using the mesh analysis. Then we get the Jacobian matrix, that is the derivative of the forward operator with respect to the conductivity. Now moving on to the inverse problem of electrical impedance tomography. Basically, this involves the reconstruction of the conductivity distribution inside the body. However, the inverse problem is an ill-posed problem. That means the small errors in boundary data can cause large errors in the reconstructed image. There are other key issues also, that is the non-uniqueness of the solution that we have achieved through solving inverse problem. And then there is low resolution of the reconstructed image. So what do we do to address the key issues? We add regularization to the inverse problem. Basically, it is used for the stabilization of solutions. Regularization stabilizes solutions by imposing constraints. Now, the nonlinear Fourier transform is a part of the approach to regularize the highly ill-posed inverse problem in EIT by applying low-pass filtering technique. This involves cutting off unstable parts of the computation and retaining stable components for reconstruction, resulting in more robust and noise-free outcomes. So now moving on to the mathematical formulation of the inverse problem. It is a nonlinear ill-posed problem. So as we can see here, we have the measured voltage data with a noise added to it. So what do we do to solve this inverse problem is we use the least squares optimization technique. So basically, as you can see, we are using the least squares optimization technique here, but it is really hard to solve. Why? Because the boundary currents depends non-linearly on the conductivity. So this means that the optimization problem is non-convex. So what do we do to solve it more easily? We take the linear approximation. That is, we use the linearized model of the non-linear forward operator. As we can see in this slide, we have linearized our least square optimization problem. There is the benefit of linear approach, that is, it leads to computational fast reconstruction. However, the linearization leads to a very ill-conditioned, underdetermined linear system to solve. There are numerical methods for the inverse problem. We can use Gauss-Newton method, but specifically we use the regularized Gauss-Newton method, which approximates the Hessian matrix and applies the regularization methods for better results. In this presentation, we have seen what is EIT, why is it important. We have seen what are the main components of EIT, how do we solve the forward and inverse problems, how we face some issues in solving the inverse problem, how we deal with those issues. So basically, overall, concluding this presentation, I would like to say that electrical impedance tomography is a very promising technology because it has both medical and industrial applications. And while it faces some challenges, particularly in the image reconstruction part of it, ongoing developments in regularization and optimization methods will surely help to overcome these issues. And at last, I'll thank you all for your kind attention.